whether this series converges or diverges. Here's a graph of f of x equals the sum from n equals 2 to x of ln of n over n squared. And if I say what's f of 1 million, it looks like it's converging. Okay, and if I define the function g of x equals ln of x over x squared, g prime of x is this green function that hits 0 right here, and g prime becomes negative. Here's where I actually found g prime. Now, why did I do all this? Because eventually we're going to use the integral test. You can come back and look at this work if you need to, but the idea is that for the integral test, the terms of the series have to be positive and decreasing. And so here's how you prove that eventually the terms are always decreasing, because g prime is always negative after this e to the 1/2. Okay, but let's look at some other possible tests. If you try the limit comparison test, this 1 over n squared might lead you to think we could use a limit comparison with a converging p-series, like n 1 over n to the 3/2. But if we try limit comparison, again, comparing the original series with the convergent p-series, what happens is that you get a limit of 0. I'll let you try to follow the work here. This means we use L'Hopital's rule to find the limit. And for the limit comparison, c has to be greater than 0, and it's not. The limit is 0. So this test does not apply. You might try the ratio test, where a sub n is ln of n over n squared. A sub n plus 1 is this. If we set this up like this, you can move these fractions together, and that limit is 1, which I've written here as n approaches infinity. And the limit of this part right here can apply L'Hopital's rule. In the end, you get a limit of 1, and if L equals 1, the series may be divergent. It didn't tell us anything. So that leads us to think, well, maybe we should try the integral test. I suppose that f of x is positive, decreasing function on the interval from k to infinity. That means we have to have some k where this f of x, ln of x over x squared, is positive. And here's the graph of that function. At 1, it's equal to 0, but after that, it's always positive. Okay, and it has to be decreasing. How do you show that it's decreasing? Well, you can take the derivative, refer back to page or board 1 for how you find the derivative, set it equal to 0. You'll find out that e to the 1/2 is where the derivative changes from positive to negative. So from 2 on, the original series is decreasing. Okay, so here's what we want to do for the integral test. We want to evaluate this integral to determine if it converges. If it does, then so does this series. How do you do that? Well, we need to find an antiderivative for ln of x over x squared. This is all the work right here, using integration by parts. There's an antiderivative. So this integral with the limit at infinity is equal to the limit as b approaches infinity of this guy, where we replace the b with infinity with b. And we already determined that the antiderivative is this. So we're evaluating that antiderivative from 2 to b, and that letting b approach infinity. If I put b into this antiderivative, I get this. If I put 2 in for x, I get this. This side as n approaches as b approaches infinity is ln of 2 over 2 plus a half. This term becomes 0 as b approaches infinity. So we just have to show what this term approaches, which is we did down here, applying L'Hopital's rule. The derivative of ln of b, 1 over b, derivative of b, and the denominator is 1. As b approaches infinity, this thing approaches 0. So the integral converges to this. It's convergent. So is the original series. And here's kind of proof of that. Here's f of x equals that integral from 2 to x. Looks like f of 10 million is about 0.8465. And here is that value that we thought the integral converged to, ln of 2 over 2 plus a half, and that matches pretty closely. And you can see as x approaches infinity, this red line gets closer and closer to here. Okay, there you go. Hope that helped. If you have any questions, post a comment.